Last time we started taking a look at Hamilton circuits and algorithms. And just to remind you what Hamilton circuits are real quick, is a Hamilton circuit is a circuit that visits each vertex exactly once. And then it returns to the starting place to end up back at the circuit. So we start and we end at the same place. That's a circuit. And then we only visit each place one time and we don't skip any. This was different than Euler circuits, if you'll remember, because in Euler circuits we had to go along each path. So this one right here, a Hamilton circuit, is more like what you do when you are trying to check off a to-do list, right? So if you have a list of errands that you're running around town, you don't need to go on every single road that's possible for you to get there, right? You just need to go to Walmart and then need to leave, and you don't want to go twice. So that's the avoiding of going multiple times. Okay, so this is more like what happens when we run errands. And we had seen several examples throughout. We've done 3 different examples of different things. And I believe that we are on this one, the number of Hamilton circuits in a complete graph. Okay, so remind you, complete graph. Complete graph means that every pair of vertices is connected by an edge. Okay, that's what a complete graph is. So if we have a complete graph with n vertices, then it will have n minus 1 factorial Hamilton circuits. Now, we've seen that notation before, that factorial notation before. And so that should sort of make sense. So think about if I had 5 points, right? 5 vertices or 5 vertexes. If I had 5 vertexes, then each of them will have 4 that will emanate, 4 different edges that will emanate out of them. That's 1 fewer, right? But each of those go to one other place that each has 4 as well. So now you've already counted one of those. So now you only have to count the 3 that come from each of the remaining points. But once you count 3 from one of the points, you're down to 2 from the next one and then 1, and you're done. And so you have a picture. I'll draw that picture of what I just described so that we can see it. And let me do it for the 5. That's fine. So here's 5 vertices, okay? So if I were to take one of my vertices and I were to take that point and connect it to every other vertice on here, I'd have 1, 2, and then I already had 3, 4. So there's 4 of them now that are all connected to that point, right? So I'll call that point, that vertice A, that vertex A. And A is now connected to B, C, D, and E. That's 4 vertices. 4 edges from that vertice, right? So I would have counted 4 of them. So I've already counted now 4 here. And I don't want to count any of the ones that I already counted again. So if we move over to B, I don't count AB because I already counted it. I would count BC. I'd also need BD, and I'd need BE. That's 3 more. Okay, so I'm not listing the corners and how many are there. I'm missing any additionals I have to draw. With C, I already counted BC. So I'm not going to count it again. I've already counted CA, so I'm not going to count it again. And I need to put in CE, and I haven't counted CD. So there's 2 more. So CD and CE get counted here. And then for point D, or vertex D, the only one that has not already been counted is the DE count at the end. So if you count all these up, you see that 4, 3, 2, 1 showing up, right? It's showing up there. So this is n minus 1 factorial. So just as a reminder, for factorial, the way that we do that is we multiply 4 times 3 times 2 times 1. That's what factorials means. And what happens when we have 4 factorial? What is that value? This would be 24. Okay, so now we're going to do an example. The thing is that if we were looking at this diagram to start with, right up here, and I actually wanted to get the value, I could just count everything. There's no need to have a factorial notation. None of this seems necessary. But what happens is because I have this description, I can actually have something that's more difficult to draw, maybe somewhat impossible to draw because it gets so messy, or I can have a verbal description instead. Do you have a question?
Yes.
Yes. Okay, go ahead.
I'm confused on where you got the 4, 3, 2, 1.
I was counting how many how many edges were connected to each vertice. This is 1, 2, 3, 4 on A. But then once I already counted it, I didn't want to count it again. And so I don't count AB again. So now I've got 1, 2, 3 over here.
So why don't you count the same one?
because I'm trying to count the number of edges. That's the point.
Okay.
And if I'm counting the number of edges, then I don't want to actually recount. I've already
I was
counted.
thinking like degrees.
Yeah. Yes, we're not counting degrees. They do all have degree 4 in a complete graph with 5 vertices. But I'm not counting the edges. I'm wanting to count the edges without counting them twice. But this is actually telling us how many Hamilton circuits too, right? And you definitely don't want to actually figure out what all the circuits are. Like, that's a very difficult task. We're going to do an example of something similar to that today, and you'll see why that's not a desirable feature to have. But we could count all the edges pretty quickly. So if we had 10 vertices, though, this one would even be difficult to draw, right? Do you know what a shape is that has 10 vertices, what it's called? It's a decagon. Yeah, it's a decagon. So think about a stop sign that has 8 sides or 8 vertices, and now make it 10 and draw it and try to connect them all like this. It's very messy. Okay, so if I did have 10 vertices, though, and it's a complete graph because it says that it is, what would I have to do to find the number of Hamilton circuits? What would it be?
10 minus 1.
10 minus 1, or 9. So I'd have 9 factorial. And what is 9 factorial? Well, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So somebody grab a calculator. I don't even know if this might be too big for your calculator. Some of them are going to let you leave it in terms of factorials. I don't have this one written down. Somebody tell me what you get.
362,880.
Okay, so that one's not too big to write down. Some of them will get big enough that you can just leave it in factorial notation, or it might even just give you the instruction that you can. So that's how many different Hamilton circuits there are. That's a lot. And that's just 10, right? Can you imagine if the graph had 20? A lot bigger, right? It's a lot bigger. Okay, so what we're going to look at next is something that you have used. I'll make up a statistic. Probably 95% of you use it. I actually think all of you, 100% have used this. You've used a weighted graph before, you just didn't know it. Okay? A weighted graph is a graph with numerical values associated with each edge. So what is an example that I'm talking about of a weighted graph? Have you ever used your phone to map yourself to a location before? Has anybody not done that? Does anybody do that on the daily? I do it quite frequently. Maybe not daily, it's probably not true, but I do it a lot. Your phone's maps uses weighted graphs. What it's doing is it's trying to find some minimum Hamilton circuit when it's doing that. So in a weighted graph, this is the Hamilton circuit with least possible weight. So what are some things that your phone is doing when it creates a map for you? I mean, I know it's giving you a direction, but how is it choosing how to send you somewhere? What kind of choices is it making or deciphering between? Turns?
Miles.
Okay, so the miles you go. It might be trying to minimize the number of miles. What else is it sometimes trying to minimize? Time, how long it takes. Have you ever had your phone change in the middle of your drive somewhere and it says, a shorter route is found? Did she tell you that? Yeah, mine too, right? It's trying to minimize time sometimes. There's another thing that will occasionally try to minimize. Do you know what it is? What's that? To avoid construction. That's usually in terms of time. They're trying to minimize time to avoid construction or traffic. Do any of you have your phones set to avoid tolls? And so it's trying to minimize something about cost, right? The cost of driving on the actual road. If it's trying to minimize time, I didn't say it that way. If it's trying to minimize mileage, that's what I wanted. Mostly what it's trying to minimize is your actual cost of your gas. That's what it's trying to minimize when it's doing that. So it's trying to minimize something. That's actually trying to find a Hamilton circuit. That's what your phone's doing when it's doing this, okay? Now, there is an algorithm, and we're going to play with it a little bit, called the brute force algorithm. This will find, for us, the minimum Hamilton circuit. What we do is we choose a starting point. We don't have to change it from the starting point to something else later. But you choose a starting point, and you list all Hamilton circuits with that starting point. Here's the problem. We just did one a minute ago that had 10 possible starting points. I shouldn't have said that. It had 10 vertices is what I really said. Once you choose that starting point, 10, then there's 9 factorial or 300 and something thousand different Hamilton circuits, and I don't want to write 300,000 Hamilton circuits out. Do you? Okay, and that wasn't very many points. But it isn't much better. I mean, it is much better, but it's still not fun if we did it with 5. We're going to do it with 5 here in a minute. Because I drew you a picture of a 5, having 5 vertices. And you remember there was 24 Hamilton circuits? Okay, so there's a bunch. Then you find the total weight of each circuit. Okay, so like your phone, you're trying to find the minimums, well, you're trying to find the total something. So your phone might be finding the total amount of time for each of the circuits it's created. Or it might be trying to find the total mileage, right? It's trying to find some sort of a total. And then you choose the Hamilton circuit with the least weight. Now, your phone, when it's doing it, it's probably not doing circuits. It's probably doing paths, right? You're trying to start somewhere and end somewhere. When you do the return, you complete the other half of the circuit. That's fine. But it's doing the same thing. It's trying to minimize this in the same way. So we're going to try one. We're going to try one with 5 points. And it looks this bad. Do I even have it copied? I don't. I better. Oh, I do. There it is down the bottom. Okay, the brute force algorithm. The first thing that we have to do is we have to choose a starting point. And it doesn't really matter where we choose. I'm going to suggest that we choose G because it's just at the top. That's the only reason. There's nothing special about starting or ending somewhere, but that's where I'm going to choose to start as G. And what we're going to do is we're going to write out all of the Hamilton circuits that start at G. There's 5 points. How many circuits am I going to write out? One more back. 24. 4 factorial for 24. So if I have 5 in a complete graph, right? This is the complete graph. So if it's at the top, I have a complete graph with 5 vertices. That's this image, basically here, right? I'm going to have 24 different Hamilton circuits. So we're going to write them out. We are not going to calculate the total weights on all 24 of them. I think that's probably an exercise in, addition that we don't need. Okay, we're not going to write them all out, but we're going to write out all of them, just not with the weights. So if I start at G, and I'm just going to write them beside each other without the arrows because I'm going to condense it. If I start at G, where could I go next? Pick me something. C. G, C, then what? E. D. Better go to F. And then we have to end up back at G. Okay, everybody good? Okay, so go a lot faster if you give me some values quicker, because it's going to take us a while to get 24 if we go that slow, right? Okay, so we're still starting at G. On every single one, we're starting at G. That's arbitrary in some sense, but remember one of the things we talked about last time, in fact, I'll flip over to it, is that Hamilton circuits are the same if they differ only by their starting point. Do you remember talking about that? That was one of our last things that we discussed. So the starting point is irrelevant to creating a different circuit. So I'm going to keep some of the letters the same, G, C, and E. I could have done G, C, E, but instead of doing D, F, G, I could have done F, D, G. Just switch those two around. Okay? This is kind of like what we were doing back in chapter 10 where we were writing an organized list of something. The more organized your list, the less likely you are to forget something. So we're going to be a little bit careful. I'm going to keep my G the same on each end. They'll start and end the same every time. So I've done CE, and then I have CE, and then I've got DF, and then I've got FD. So I can't do CE again. Now I have to do C something else. So pick one. CF. So if I do CF, I could do DE, or I can do CF, and then I can do ED. But maybe I don't do GCF. I do GC something else. What else could I do is next? D, GCD. Greatest common divisor. I'm teaching about that in another class recently. GCD. But then I could do FE. Or I could do the GCD and I could do EF. Okay, Okay, so I have manipulated the third letter as many times as I can now, right? There's nothing else to manipulate within the third letter. First and last are staying on the same all the time. Now I'm going to change it from GC to G something else. G what? What do you want to pick? GF. We'll do GE next. So GF. So then after F, what could I pick? What? E? D, C. Am I ready for G at the end? Is that enough? Yeah, it's enough. But I could have done G, F, E, and then C, D, right? I could have done those in that order. I got 6 of them that started out GC, right? So there's going to be 6 of them that are going to start out GF. And there's going to be 6 that are going to start out GE, and there's going to be 6 that are going to start out GD. Does that make sense? We've got to have the same number in each of these reiterations. Okay, so GF, let's see, I could do GF D, C, E, or GF C, I'm sorry, D, D, E, C. Or I need 2 more GFs. GF, what else? What am I missing? GFC. GFC, E, D, and GFC, D, E. That's those 6. So I've done GCs, I've done GFs. Now what are you going to do? GE. So all of these are going to start out GE. You might as well, I'll go ahead and do them all this time. I've got 6 of them. What do you want to do? And they all end in G, but what's going to come after E? F. Okay, there's 2 that are going to start out F. And there's 2 that are going to start out D. And there's 2 that are going to start out C. You like how I'm shortcutting this? You can do that, right? After the F, I can have DCG, or I can have CDG. After the D, I can have FCG, or CFG. And after the C, I can have FDG or DFG. Okay, we've got 1/4 left to go. I've got 3/4 of them written down. What's my last set going to be? G what?
D.
Is that the one I'm missing? GD? Okay, GDs. And so we need to pick a letter next. C's. E's, F's. Let's do it like that. Okay, after C, I can do EF or FE. I can do CF or FC. And I can do EC or CE. I think that gets the rest of them. Do you want to do it with 6 corners? No, you do not. 4 is not so bad. We could do 4, right? It'd be fewer. 4 would give me 3 factorial. What's 3 factorial? 6. 6. We could do that one. Let's do that one, right? Let's do 4 vertices. Let's not do 6. All right, so what does the brute force algorithm say? Well, it says we should have listed them all, and we did. I'll put it back in just a second. We listed them all, right? Yeah, I'm going to get them back there just a second. We listed everything. So we've done step 1. Okay, so step number 2 says that we're supposed to actually count them all up. We did step 1 and 2, sorry. We're supposed to do step 3. We're supposed to count them all up. So we're going to take just a few of them and try that. We're going to count it up. So I would like for us to try that. Let's just take the first one. How about we do the first one of each list? How's that sound? We're not going to do 24 of these additions, but we could do 4 of them. All good with that? Okay, so do you see the numbers along each of the branches? Those are the weights of each of our, they're not branches, they're called, we'll do branches later. They're edges. So along each of the edges, those are the weights. It's the miles, or it's the cost of something, or it's the time of something, if you're thinking about it like your phone with it calculating the map. Let's do this first one down here, GCEDFG. So what we need to do is we need to find out the sum, like all of the different values, and add them together along each of those edges. And I'm going to write it in yellow over to the side to try to keep it distinguished. What is this? What is the length of GC? What is the weight? It's 10. And then we go from C to E. What is the weight of CE? It's 15. And then E to D is 10. D to F, 21. And then F back to G, 15. Okay, so somebody grab calculator. Let's add those up. Because I let you guys choose all my points, I don't have any of these added up. We're just going to have to go with it. It's 71? Fantastic. I've got 3 people saying 71. Must be right. I mean, that's not a true mathematical statement, but we're going to pretend for a minute it works. Okay. The next one, which I don't really have space to do here. Let's just go to the top line first, and then I'll move some things around. All right, G, F, E, D, C, G, the one that I have on the very top. Let's do that one. So what is GF? 15. FE, 17. ED, 10. DC, 12. And then CG, 10. That one was nice because it was around the edges, right? On the outside. So what do we get when we add this one up? Do you have 64? 64? Yes, no? Yes? I got it now. It's good. Good, good. All right. Let's just make this one a little bit smaller, and I can again add it beside it. Okay, so we'll do this one that's sort of in the middle that I'm shrinking right now. G, E, F, D, C, G. So what is GE? What is it? 13. EF, FD, FD is 21, is right? FD is 21. DC, that's 12. And then CG is back 10. $73. Okay. And then our last one over here that I'll shrink as well. Okay. GD, 13. DC, CE, 15. EF, and then FG, 15. That might be the messiest one we've got to add together. It definitely was. I think it's 72. Is that what we have? 72? Okay. So we could literally do this 24 times. And in doing it 24 times, we would find the one that was the smallest. And there might be more than one that's actually the smallest. Agreed? We could do that. That's really not fun. And the reality is that while your phone is very capable of doing a brute force algorithm, it doesn't do it either. Have you ever had the experience where you're looking at the map and you're like, that just doesn't feel like that's the way that I would normally go, and you force the change in direction somehow, and the time went down or the distance went down, and you're like, what the heck? That didn't make any sense. It was supposed to give me the best option. It's because it's not doing a brute force algorithm either. What your phone is doing is what's called an efficient algorithm. So an efficient algorithm in general is simply an algorithm that doesn't take very much time to do. And brute force algorithm is not that. It's very time consuming. And if you think about what your phone is doing, right, in terms of these corners and everything too, like all the different ways that you could really get from here to Edmond, you've got to be kidding me, right? Like it's not really checking all of them. It's not efficient. So what happens instead is that we usually are trying to look for an approximate algorithm. Algorithms that don't take the computer too much time to do, but they still give you a reasonably good solution most of the time. Reasonably good is good enough to live by for lots of things, especially with traveling from one place to another. And reasonably good is not good enough to live by in terms of, your faith or something like that. But in terms of driving your car from here to Edmond, I'm good with reasonably good. So the algorithm that we're going to see used instead is going to be called the nearest neighbor algorithm. The next slide, are we ready? Almost. Okay, the nearest neighbor algorithm on the next slide says the following. We choose a starting point. Okay, that's fine. And we look at all of the different options that lead away from that starting point. And from there to the next vertex, we just choose the one that's the smallest. And then after we look at that one, we don't go repeating anything, right? We don't go backwards. We look from there forward to the next smallest that connects to that one. And we keep doing this process all the way until we get back to the starting vertex. And the reality is we may not find the absolute minimum Hamilton circuit, but it's going to be pretty close. It's going to be pretty good. It's going to be good enough because it's more efficient. Okay, so we have an example of this. We're going to do that example first, and then after we do that example, we're going to go back to the problem we just did and see how that would have worked out and how much easier and simpler it would have been. But let's do the example that's in your notes first, example number 7. We're going to use the nearest neighbor algorithm to determine an appropriate solution. Notice that it's not the best solution, it's an appropriate solution to the problem of finding a minimum Hamilton circuit for the graph. In each case, find the total weight of the circuit found. So I am going to list this out. I'm trying to try not to mess up my diagram since I've got two parts to it. I've got part A, which is starting at F, and part B that's starting at G. But so if we start at F, there are 3 different edges that are connected to F. Which one is the smallest weight? It is H. So we're going to go from F to H first. And how many, what's the weight of FH? It's 2. So I'm just going to write down 2 next to it. After I go to H, I'm clearly not going back to F, but I'm either going to up to I or over to G. Which one's the smallest? I. So I'm going to go up to I. And what's the weight of that option? That's 4. Now, after I can't go back to F because I haven't visited everywhere yet. So I have to go down to G. At that point, I don't have a choice. And the weight along IG is 3. And then G takes me back to F. And the weight along GF is 6. And we add 2 plus 4 plus 3 plus 6. What do you get? 15. Okay, it may not be the absolute best solution, but it sure was faster than finding all the others, right? Okay. It's 15. It's reasonably good. It's good enough to live by. right? It reminds me of what happens when our children do some Bible memorization stuff, both at their school and at church. And a lady at our church phrases it like this when they mess up a word: that was good enough to live by. You didn't get it word perfect, but it's good enough to live by, right? This is good enough to live by. It's not that important for us to find the exact best option all the time. We're going to start at G, and we're going to do the same thing. If I start at G, where will I go first? I will go to I, and that value is 3. After I, where will I go? Down to H, and that value is 4. After H, at that point, I don't have a choice. I have to go to F. F is 2, and then after F, I return to my starting point, FG, and FG is another 6. And I happen to get 15 again. That doesn't always happen, starting at a different point, but this one did. Okay, so let's go back real quick and try the same thing that we did here on this graph and see what would have happened. We're going to start at G as well, and I'll write it along the top. So this is my nearest neighbor algorithm. If I go from G, I can highlight this one. If I go from G, green, where would I go first? G to C, G to D, G to E, or G to F? G to C, that's my least one right there, right? You can see that pretty well. Good. All right, so that's 10. Okay, after C, where am I going to go? C to D. That's down. That's 12. Okay, after D, where am I going? E. D to E is 10. Okay, I'm running out of options. Where am I going to go after E? It's got to go F, right? Like that's my only choice because I can't go back to G. It'll be done yet. So I would have E to F. That's 17. Is that right? And then F goes back to G and it's 15. Okay, so let's add up 10, 12, 10, 17, and 15. And what do we get? What is it? 64. 64. And I think I had a 64 out here somewhere. I think I erased something accidentally. Was this one over here 64? I don't know where that 6 went. I think that was 64. So we actually did find one that matched what we had done before. It's possible when I do that, I don't actually find a number that's smaller than what I did. That would be a possibility, right? Especially if I found all 24 of these guys. This won't necessarily find the best choice, but it'll find one that we can live with.